I want to do a short video on a one-sided hypothesis test for proportions. Okay, we've done hypothesis tests for means, and when we did those, we saw that depending on whether we knew the population standard deviation or not, we used either a z-test statistic or a t-test statistic. What's nice about proportions is it's always going to be a z-test statistic. So we don't have to worry about that either or situation when we talk about hypothesis tests for proportions. So let's go through this one. This is an example. This is pretty much a generic example here. I'm not giving you a real situation. I'm just giving you the outline, the numbers, the way to conduct the test. We know how to conduct a hypothesis test, the 4 steps that we've talked about. So in this case, we have a random sample of 60 observations. Think of the binomial distribution, either a success or a not success. So, a yes/no question, something that only has 2 possibilities. That's what these proportions are going to be. They're going to be the proportion of individuals, again, remember people, places, or things, that either this or that. It's a proportion. It's either or. So in this case, we have 60 observations, and it resulted in 17 successes, which we're going to call a success. We don't know exactly what the situation was or is. We just know that there's 60 observations and 17 successes. So that gives us our sample proportion of successes, right? Or that's the first thing we got to do, is come up with the sample proportion of successes. 17 over 60. And I'll be clear about what to round to. We'll round this to 3 decimals, and it's 0.283, 0.283, and our sample size is 60. That's all we need to know when we're doing hypothesis tests for proportions. Those are the only things we need to know, and we need to know what we think going into the test. So we took an observation of 60, we got 17 successes, and we're going to test the claim. The claim is going to be the null hypothesis that the unknown population parameter is more than 0.18. So that more is the clue that we're talking about a one-sided alternative, right? So you're looking for words like this in the description to tell you if the test is going to be 2-sided or 1-sided, and if it's 1-sided, what direction we're looking at. So we're looking for evidence. Remember, we're looking for evidence for the alternative hypothesis. Again, innocent until proven guilty, the jury example. The null hypothesis is innocent. The alternative is guilty. We need overwhelming evidence determined by our alpha level. That's going to be the level of evidence required for us to overturn that null hypothesis. So we go into the test believing that the unknown population parameter, P, the population proportion, is equal to our null hypothesis value, P sub 0, and we're going in thinking it's 0.18 or 18% successes. We're looking for evidence that it's more than that value of 0.18. That tells us it's a one-sided test to the right. This word more gave us that information, and we were told to use an alpha level or a level of significance of 0.01. So that is step 1. That's how we want to see step 1 written out clearly, details, correct notation, not an equal sign, colon, this is the equal sign, this is the equation, this is the inequality. It's not null hypothesis equals this. It's the null hypothesis is a statement. This is the statement of the null hypothesis. This is the statement of the alternative. This is the direction of the test. This is the level of significance. All right, so again, what's nice about these proportion tests is it's always going to be a z-test statistic. And the z-test statistic takes this form. Okay, all these formulas are on the sheet that I gave you. I don't want you to use your calculator to come up with these values. I want and will need and require you to show these 4 steps whenever we do a hypothesis test. So it's nice to use your calculator to check your answers, but I don't want you to just use your calculator to do the whole test. The whole idea of this class is to understand the theory behind confidence intervals, hypothesis tests, not just to plug numbers into your calculator. Okay? So first step, form the hypothesis. Second step, calculate the z-test statistic. We have the p hat, we have our null hypothesis value, and we have the sample size, and that's all we need. Now, I mentioned this before, but notice very importantly here, the denominator of the z-test statistic is very similar to the standard error of the sampling distribution of p hat, but it differs in a very important way. For the confidence intervals, we used p hat here and here. For the z-test statistic concerning hypothesis tests, we're using the hypothesized value here and here. So very important, a very common mistake on these problems is people will use this p hat here. That is not correct, and your answer will be wrong. So make sure you understand that. The denominator here is the square root of the hypothesized value times 1 minus that hypothesized value divided by the sample size, the square root of that whole thing. So we plug those numbers in. P hat, hypothesized value 1 minus the hypothesized value over 60, square root of that. If you take this difference, you're going to get 0.103. If you calculate this value by itself, you should come out with a number rounded to 4 decimals of 0.0496. You take that ratio and you come up with your z-test statistic, always rounding to 2 decimals and rounding correctly. Please round correctly. You get 2.08. And remember what that says. Again, if the null hypothesis is true, then when we take samples of 60 from that population, we are going to get a value this far away from our hypothesized value. This tells us that the value we get is 2.08 standard deviations from the center of what would be the sampling distribution, the center, if this was true. This would be the center of the sampling distribution. We got a value that's over 2 standard deviations above that hypothesized value. Well, what's the probability of that happening? That's the third step. The p-value is the probability that we get a value greater than 2.08 from our sample. So we calculate that value. In a standard normal table, always a standard normal table for proportions. So the probability that we get a z-value that large or larger. Okay, this is where we use our tables. I use the complement method here. You can either use the complement method or the symmetry method. Either one will get you to the same result. I use the complement method here. The probability greater than this number is 1 minus the probability less than that number. We look up this number in the table. I'm not even going to show that since we've done that so many times, right? We know our tables. We know how to look values up in our standard normal table. You look up 2.08, you're going to see this number. You subtract that from 1, and you get your p-value. So again, what this says is if our null hypothesis is true, we're going to get a value this far away from that, from samples of size 60, less than 2% of the time. But our alpha level is 0.01, right? Our alpha level is 0.01. So even though this is a small number, we're only going to get a value this far away from this percentage of the time. It's still greater than our alpha. 0.0198 is still greater than our alpha level. of 0.01. So remember, that's the conclusion, right? That's what our conclusion is based on. We compare the p-value to the alpha level. Our p-value is greater than the alpha level. So that leads us to the conclusion that we do not have sufficient evidence to suggest that the unknown population proportion is greater than 0.18. We do not have evidence to change our mind about the null hypothesis and go with the alternative. We're going to stick with the alternative because we did not have enough evidence to change our mind. So once again, 4 steps, always 4 steps. Nice thing about proportions is it's always a z-test statistic, and you're always using the standard normal table to look up your probabilities to get the p-value, and then you make a conclusion in step 4. So that is a hypothesis test, a one-sided to the right hypothesis test for proportions, and we will do more examples as we move along.